So now we will talk about random graph. So in previous section so far, we often generate a graph by taking n vertices, which we usually identify with numbers from 1 to n. And for each pair, we include an edge with probability p independently. And that's a random variable, and as well as a probability distribution. In this probability distribution, we show that with positive probability, certain property holds. Then taking such a graph, is what we wanted. So that was often what we did. So this probability space is very useful. As we have seen so far, using this, we have considered lots of examples. So study about this probability space itself also is very important because, it is, partially because it is very useful to generate lots of examples for many problems. Okay, so we want to consider its probability space, and then we want to study about this. So for that, let's define some terminology. One of the terminology we want to define is the following. We're given a sequence of probability space. Say, let's write this sequence as omega n. Let Qn be the probability that certain property Q holds in this omega n. And what we say is that we say this property Q almost always holds if this probability as n goes to infinity, this probability goes to 1. And we say that it almost always holds. So here, note that we are considering sequence of probability space instead of one space. Because oftentimes, as we've seen before, this kind of construction, when we consider this kind of random graph, we assume n is large. But every time for a certain property, we have to take n this large, and then for a certain other property, we have to take the n this large. And then keep changing this n is inconvenient, and that's often we encounter the problem of mathematical rigorousness. So, and for the further discussion, it's much more rigorous if we consider a sequence of probability space where the n is increasing, so n tends to infinity. Then, we in this way, instead of considering one probability space, we consider in sequence. Now we don't have to, worry too much about whether n being specific value or whether n being large enough or not. So with this definition, now we can define our probability space. So let P be a function of n. And we define the probability space. We write G and P, which is on graphs with vertex set bracket n as follows. But we do take any two vertices, they form an edge with probability P independently at random. So this is a probability distribution over all graphs on this bracket N. In particular, this is a labeled graph. So its vertex are labeled. So there could be different labeled graph which are isomorphic. This is not the equivalent class over the this is not the isomorphism class of graph, it's a labeled graph. And this is the probability space. And we also denote the random variable. So this is the graph we obtain from this probability space, drawn from the above probability space, and we also write it as a GMP. So this GMP is a probability distribution as well as the graphs that we obtain, the random variable. So sometimes we treat it like a graph, sometimes we treat it like a probability distribution. But I mean, we abuse this notation by denoting two different things with the same way, but it will be clear from the context. And the sequence, say GNP with overall natural number is known as a standard random graph or binomial random. The binomial random graph model. Okay, so I mean, also we don't necessarily write it as a sequence. We also denote the sequence as GNP. Okay, so that's a binomial random graph model. And this name suggests that, there could be other random graph model as well. So this is standard random graph, and there are non-standard random graph model. Of course, there are many ways to consider. I mean, there are many ways to define this probability space, and then each of them has its own advantage in dealing with a certain problem. And maybe let me introduce one more thing that's very natural. Let's say M is a function of N. And we can consider the probability space. G and M is assigned to each graph with the vertex set bracket N and M edges. So there are many graphs with any such graph. And then how many such graphs? There are, all of such graph, we give the same probability measure. The probability, bracket N choose M to the -1 with this capital N, not bracket N, so this is capital N, is the N choose 2. So that's as a labeled graph. How do you find such a graph? You choose M edges. out of n choose 2 possibility. That's how you choose this M edge graph. And then, among all of them, we give the same weight, same probability. And this is called the uniform random graph model. But so these two are the most basic random graph model. But these two are mostly same. So for most cases, we can focus our attention to the binomial random graph model. And because why? Essentially what holds the properties that holds for binomial random graph model also holds for this uniform random graph model and vice versa. What it means? We say that a graph property Q is convex if it satisfies Q whenever F is subgraph of G and H is supergraph of G, and both F and H satisfies Q. So most of interesting properties are convex. For example, synclinarity. It's a planar graph, and it's a subgraph of planar graph, then G is the planar graph. And the property of containing triangle. If F contains a triangle, then G also contains the triangle. Property of having Hamilton cycle. If F has Hamilton cycle, G has a Hamilton cycle. So most of the interesting properties are convex. And for those, we have the following theorem. If Q is a convex property, and when P satisfies that essentially it's not smaller than some large constant times n square, or not bigger than 1 over large constant times n square. So those are like too small p and too large p, except those cases. And this G and P almost always satisfies Q if and only if the following holds for any fixed x, this G and M almost always satisfies Q, where this M is P n choose 2 plus S times, square root of P or minus P n choose 2. So it's not too important of what this expression is, but what it essentially says is that if certain property almost always holds for this, then it translates to M, as long as M is very near to this P n choose 2. Conversely, if this satisfies the property for all M, which is very close to this, and that translates to here. So we can just focus on one of them. And maybe I forgot to mention that we have defined this almost always. And then this GNP is a probability space as well as this random graph. And then we want to study it by identify which property holds for them. But when we say a property holds for them, it's not just one graph, it's probability distribution. So that in order for that, we say that almost always hold. Those that almost always satisfy certain property. So study about this GMP is about for what property Q, this almost always satisfies it, or almost always not satisfied it. So that's what we want to study. And regarding that, this theorem tells us that binomial random graph model and then uniform random graph model are not too different. So we can just focus on binomial random graph model, and the result of our the uniform random graph model follows. Okay, I will now prove this. And now what? Our question is that for given property Q, we want to check whether this almost always satisfies certain property Q. So this is what we want to check. But here, it depends on this value of P. So for what value, for what P does it almost always satisfy Q? That's the question. And again, this P could be anything. So there are many functions that you can take. So in order to completely answer this question, we want to focus on the natural graph property. For example, if this Q is what? Say that the graph has even number of edges. And for whatever, for most of the P, unless P is extremely small to make sure that this is almost always empty or almost always complete graph, then this is possible. It almost always satisfies Q or almost always not satisfy Q. That's possible. But for otherwise, if it is not really trivial distribution, then no matter what P is, it's almost always, almost the case that this is not true. So this is too sensitive. This property is too sensitive, so that in this binomial random graph model, this is not really meaningful. So we want to focus on more natural property and more interesting property for this random graph model, and which is this monotone property. So monotone property is a graph property which is preserved by addition of edges. So, for example, property of being connected. If you have a connected graph and you add an edge, it's still connected. For property of having triangle, you have a graph with triangle, you add an edge, it still has triangle. For property of Hamilton cycle, having Hamilton cycle, you add an edge, it's still Hamilton cycle. So you can consider many such property. Okay, so for this monotone property, our intuition is that if we increase the value of P, then it's more likely to be satisfied. This property is more likely to be satisfied. And if we decrease the property P, then it's less likely to satisfy. So there must be this value of P, there must be certain threshold that above this or below this, the behavior changes. Maybe, there is this thin threshold that here it's almost always holds, and it's almost always not holds. Or it could be that there are some bands that here almost always hold, almost always not hold. Then here we don't know. Not we don't know, but it's it holds with probability 30% and 70% it doesn't hold. So there could be different. Anyway, for this monochrome property, it's intuitive that once this property holds at here, when p has values a n to the 1 negative half, for larger function, it should be also almost always hold. If it doesn't hold here, or it almost already doesn't hold, and for lower value, it's also like that. So, this monotone property is, it's a good property to consider this question, because we don't have to consider all function p. As long as we specify certain threshold, then all functions above here, all functions below here are automatically solved regarding this question. So we can define this concept of threshold. So we define a threshold probability function for a monotone property Q in this G and P is a function, say T of n, satisfy the following. So what is G and P? Almost always they do not satisfy somehow. So there was technical problem. So almost always do not satisfy Q when its probability function is going, much smaller than the Tn. So Tn divided by Tn go to 0 as n goes to infinity. And GNP almost always satisfies Q when Tn over Qn, Pn over Tn goes to infinity as n goes to infinity. So this is a threshold function, and we say that the sharp threshold function for again monotone property Q in PNP is a function Tn satisfying again the following for any positive epsilon. So again GNP almost always do not satisfies Q if what? If Pn over Tn is smaller than 1 minus epsilon, and GNP almost always satisfy Q if Pn divided by Qn is bigger than 1 plus epsilon. So later cases, more sharp, right? Here, this function has to be much bigger than this. This time some large constant is not sufficient. This time some function which goes to 0, and this time some function which goes to infinity is required. But if this is much more sensitive, then we say this is a sharp threshold. Note that this is a sharp threshold function and a sharp threshold function. For example, if Cn or 1 over square root of n is a threshold or sharp threshold, then what? For example, we immediately know that this is also threshold. And threshold-wise, I mean, if in terms of the first one, even 2 over, it is the threshold. 2 over square root of it. So, threshold function is not unique. And if this is sharp threshold, and then this is also sharp threshold. So, sharp threshold function is also not unique. But essentially, if you find one sharp threshold function or one threshold function, then you immediately understand about what threshold function has to be. So you immediately understand all other threshold function as well. So, because they give you a growth rate, and as long as some function has the same growth rate, then it is threshold function. And what we want to do is we want to find the goal. Our goal is to find the sharp threshold function for being collected. So this is very natural monotone property, and we want to consider it. As a warm-up, let's show that the threshold function must be some function that goes to 0. In other words, if we just consider fixed constant p between 0 and 1, this constant function always the binomial random graph, BNP, is almost always correct. So any constant p is above the threshold if the threshold exists. So what's the most easy thing to consider? When does this G become disconnected? If there are two vertices and then there are no edges between them, then this is disconnected. So we also have to consider this edge code, say S and S complement. And how many choices are there? When this S has size K, then what? The number of edges, possible edges between there are K times M minus K possible edges. In this edge code. If all of them not appearing, as the probability is that 1 minus p to the k m minus k is the probability that none of them is an edge. So what do you know? The probability of being disconnected, let's write Qn, probability of disconnected is what? It's at most. You take n choose k choices of S, and then as this and this are the same edge code, you divide by half. And let's say k is from 1 to n minus 1. You will choose an edge code. And for the probability that they form disconnected, the no edges between them is this, and this is what? Just because of the symmetry on here, it is n to the k times 1 minus p to the k n minus k. So we can write it this. But what do you know? By restricting this k between here and here, we know that this is bigger than n over 2. So this is what? N to the k, you can write it. So this is m mod n to the k, and this is what? 1 minus p to the n over 2 to the k. So this is what? N times 1 minus p to the n over 2 to the k. Then, for large n, n times 1 minus p to the n over 2 is smaller than 1. So this is the polynomial function. This is the exponential function, both going to 1, going to 0. So this is very small number. Then what? This is smaller than this geometric series. So this number is smaller than 1, and then you keep taking this. So we have Qn is smaller than x over 1 minus x, where this x is n times 1 minus p to the n over 2, which equals to 0. So this shows that Qn approaches to 0 as n goes to infinity. This verifies that it is almost always connected. Here, I mean, this analysis was not tight at all. I mean, here, aperture here is okay, but somehow this is, we just use this is smaller than 1, but this is not just smaller than 1, it's decaying very fast. And the computation was very straightforward. And I mean, the same analysis might hold even if you don't take p as a constant. And if this is a function which goes to, 0 in a appropriate speed, then this analysis would still hold. So this analysis is not tight. But as I mentioned, we will try to find the threshold for its connectedness. So we want to find the best key which makes this statement hold. For that, we need to first collect some tools. Some further probabilistic tools are needed, and then we will collect them in the next video. Okay, then I will see you in the next video.